Hi everyone. Thank you for joining us today. Welcome to our workshop. I would like to talk about fiber optical sensor we developed and applied in resin transfer molding, in short RTM, and structural health monitoring, in short SHM. First, I will say a few words about Morpho project. Then I will discuss fiber optical sensor we used in this project that is based on fiber Bragg gratings. Finally, we will discuss application of these sensors in composite manufacturing and structural health monitoring. The Morpho project, supported by Horizon 2020, brings together 10 partners from 6 countries. The goal is to design, test, and validate processes for manufacturing, monitoring, and recycling of advanced aeronautical components such as fan blades. A key part of this project suggests the development and integration of advanced sensor technologies to track real-time life cycle of aeronautical components. We develop and integrated sensor into specific section of the fan blade. You can see here on right. This section that called foreign object damage panel. The integration sensor were used for RTM process to improve composite production process, for SHM modeling to optimize manufacturing and performance, and for SHM to enable real-time structural integrity. To discuss fiber optical sensor technology, let's look at the main benefits of using them, and to understand what is fiber optical sensors. Fiber optical is made of core, cladding, and coating, polyamide coating. This tool, fiber optical, is ideal to transmit information with minimal loss. It's ultra thin, just about 1/4 millimeter, and it's ultra light. On the microscope, you will see on this picture, for example, the thickness is similar to that of human hair. Here, this unique scattering structure in the fiber center is a fiber Bragg grating we will now discuss. This structure we use as a sensor element in the project. A fiber Bragg grating is a small periodic structure in the core of the optical fiber that changes its refractive index when broadband light enters the optical fiber. The FBG, the structure, reflects a specific wavelength known as a Bragg wavelength. This wavelength is determined by this formula, including effective refractive index of material of the glass of the core, and grating period. Setting this grating period, we can tune each grating in such a way that it reflects its own part of the broadband light source, allowing us to address each grating individually. The main advantages of the fiber Bragg grating technology, its ability to multiplex. We can realize a lot of sensing points in one fiber that is highly sensitive to temperature and strain, which was crucial for our application. To create Bragg gratings, we use femtosecond laser technology and direct writing methods, which make it possible to focus laser beam directly in the fiber core through its coating. This method works with the standard telecom fibers and provide great flexibility. However, it required precise control of the beam movement and focus. In addition to creating the grating in the optical fiber, we also need to process the signals that are generated from the FPGs in the fiber. For this, we use special grating in the same fiber, which act as a dispersive element, directing the signals or the light parts from the FPGs out of the fiber. You can see it here on the detector. This approach allowed us to build a compact and robust interrogator with high spectral resolution. For example, a single small device like this with 4 fiber ports can interrogate, depending on sensing dynamic range, up to 120 FPGs sensor. As we already discussed, FPGs are sensitive to changes in temperature and strain. The reason is that the fiber Bragg grating depends of, as I said, refractive index of the fiber and grating periods. An increase in the temperature, for example, leads to shift of the Bragg wavelengths to the higher value. Because the refractive index will lower and the grating periods is higher due to the fiber to expanded. When the temperature decrease, we have opposite process, of course. This relationship can be described linearly for small temperature changes, and for the large changes required more complex models. Mechanical stretching or compression also cause a shift in the wavelengths, and this effect is also linear. Thus, integrating gratings in composite material allows us to measure any deformations in the structure and temperature variation. The production of composite materials involves many processes. For example, starting by manufacturing of the preform. Then, in our case, sensor integration in this preform. Then next, closure of the mold and compression of the preform, resin injection, RTM process. After that, demolding of this part. Then for SHM analysis, we add additional sensors on the surface of the part, and finally we bend and load this part in frame of SHM analysis. Let's discuss each of them in more detail. Before using fiber Bragg grating, we first specified the position. You can see it here with preform. and integrate them and tried to integrate them with minimal impact on the final components. Sensor placement was based on the simulation results from other project partners, and mold integrated sensor positions. We also ensure compatibility with manufacturing process. It was a challenging task that required significant optimization of both sensor, fiber optical sensor, and integration process. For example, from marking these sensor points to placing inside the structure, inside the preform. For example, you can hear one of the sensor fiber integrated in the preform. In total, we integrated around 70 FPGs into each FOD panel. My colleague Andreas Krenz from Fraunhofer IFAM Institute, he is pictured here, will share more details on the sensor integration. And Dr. Nikos Pantelelis will explain the mold integrated intelligent sensor technology for composite molding monitoring later at today's workshop. After integrating the FPGs in the preform, our first step was to place sensor equipped preform in the mold, close it, and apply pressure while analyzing sensor data from our integrated fiber optical sensors. This process helped us identify weak areas and make necessary optimization. As you can see on the slide, we get two types of signals from our sensors. Wavelength shift. This is our primary indicator for decreasing strain, for detecting strain and temperature changes. And the additional information was intensity of the signal. It was helpful to identify, for example, fiber bendings at such areas in the preform. Here is a measurement example from both values. As you can see, after the mode closure, he's open, and at this point, the mode was closed. There are no wavelength shift, indicating that no compression or no extension was applied in the grating. However, small changes in the peak intensity can be observed in at some sensor fibers. Which may indicate that small bendings or affectings was applied on the fiber. After we closed mold with sensorized preform, we compressed the preform while collecting the sensor data. This measurement allowed us to validate the integration technique and detect any fiber breakage. It was very crucial information in the early stage of the project for optimization sensor integration. For example, you can see it here that after compression, we have some signals changes. And for example, from 2 of 6 fibers at this panel, 2 or 3, I think, we didn't have signals at a specific stage. So we can, after the compression, analyze the sensor data and see how we can optimize the sensor integration. After validating the sensor integration, we injected resin into preform while monitoring the sensor data. As expected, we observed that when resin filled the section with a preform with integrated sensor, for example, the first of the FPG, first FPG placed in optical fiber, we can see increasing of the signal. Here's a stable condition of the signal. For example, here was the starting of the injection, and then the resin arrived the sensor, the FPG, the wavelength shift, or our signal is increased. When the resin arrived the second FPG, we can see it here, it's also increased, and so we can detect resin arrive at each FPG. Thus, by monitoring the data at each grating, we can track when the resin arrives in a specific section over time. For example, here on the right, you can see the graph where the arrival time is a function of FPG position. Embedded FPGs, by receiving this data of multiple fibers distributed within the structure, we can obtain real-time information on resin flow inside the preform, shown on the right. For example, each sensor here, for example, we get information from 5 optical fibers with 8 FPGs. Each sensor indicates its arrival time as resin achieved it, reacted. This information allowed us to optimize and improve injection process and detect actually it can detect defects, and it's useful for online quality control during manufacturing. After manufacturing the FLD panel, additional FPGs, optical sensor, and printed piezoelectrical sensor were installed on this surface. In addition to embedded optical fiber, you can see a full sensorized FLD panel with embedded and surface optical fiber, also with the piezoelectric sensors, printed piezoelectric sensors. Dr. Ingo Wirth from Fraunhofer IFAM Institute will discuss this unique technology of the printed sensor later at our workshop. The fully sensorized panel was used for structural health analysis, for example, for a 4-point cycle load test to measure stress, strain, and predict degradation in the structure, demonstrating the effectiveness and that the integrated sensor is useful for diagnostic and prognostic purpose. On the right, you can see the setup for these measurements, and some of the measurements results where the cycle bending quad was applied. Our colleagues, project colleagues from Delft University of Technology, who are applying these optical fibers and other sensors for SHM, we'll discuss this significant topic of the project, advances in SHM, in aeronautical, in more detail at our next workshop, which I highly recommend attending. Let's summarize our work. First, optical fiber with FPG sensor were integrated in the composite part of NG fan blade with minimal impact of the structure of the host material. Next, fiber Bragg grating successfully monitored the RTM process by detecting the presence of resin during injection. And embedded fiber optical sensor in composite structure enabled real-time health monitoring by detecting stress, strain, and damage. Finally, in the future, a more detailed examination of individual sensor points or FPG sensor will be conducted during the RTM process to validate each of the sensors. We also now working on temperature measurement. Are working on the temperature measurement for curing and heating of the preform, and in the future we'll present these results. Thank you very much for attention, and as was said, you can, if you have any questions at the end of our presentations, please don't hesitate to ask.